All right, so let's start our class. The agenda is on the screen right now. A lot of things going on. I know that you're busy with many different things. Hopefully, the agenda helps. If not, please go and look at the information. I've been updating the information table on Blackboard. And I removed the date, not the dates, I'm sorry, the topics to ensure that nobody gets confused. If you see a different topic, the topics is whatever we're covering is on the agenda, but the dates are there. Okay, so we're gonna hopefully finish risk assessment. If not, it's fine, but we're gonna be we're very close to finish. And then we have our kinetics mass balance quiz later at the end of the class. The risk quiz is gonna be on November 2nd, and your midterm is going to be on November 4th. So it's pushed a little bit more, and a holiday is coming. November 11th is a holiday, so we're gonna take a little break. And then there is another thing that I want. It's not in there. I'll keep reminding you on November 16th. It's a Monday. The class is not gonna meet in Zoom. It's gonna be an hour given to you to work with your team, making progress on your project. So please do not wait until then to do progress, but plan, because it's one day that you're gonna have the whole class time to meet via Zoom if you want, or any other way, not in person, with your classmates, and dedicate that time for the project. And I'll remind that, but please make sure that you meet during the class time, because I don't want to have conflicts of time that you guys met at a different time. And I'll be reminding you of this as time comes closer. Alrighty, so let's move with our topic of risk. Hopefully we can finish it today.
Professor, can I ask you a question?
Yes.
Is the quiz at the end of the class, is it the same as last time where it's like 15 minutes and then 5 is to upload?
Oh yes, and I'm gonna go through that again when it's time for the quiz.
Okay.
All right. Yep. So it's gonna be pretty similar. Pretty similar. Let me see. iPad now. It's coming on. Can you see it? All right. Okay. So last time we were talking about the how do we call these plots? And check your notes. How do we call these plots? No idea?
Aren't those the dose responses for acute and chronic toxicity?
Yes, thank you, Edgar. So I wasn't asking specifically. So your answer is right on the dot, like for both the dose response curves for either chronic or toxicity. I'm sorry, chronic toxicity or acute toxicity. Yeah, thank you so much, Edgar. So we talk about this, and we ended up with these two formulas, very important. The general definition of CDI, and then the specific calculation or determination of CDI if we're talking about ingestion via drinking water, or exposure due to inhalation if it is a gas compound. So I said that we're going to be talking about two more formulas. Please keep these formulas handy, because we're going to be doing problems and we need them. I'm not going to be, it's going to be hard to go back and forth on the screen. I could do it, but the classroom doesn't run as smooth as when I don't show them again. So please keep them handy. If needed, we can come back, no problem. So the next thing that we need to talk about is how do we measure the hazard when we have exposure to non-carcinogens and their effects. So let's put it in here. The hazard exposure or non-carcinogens effects. And the fact that it's a non-carcinogen doesn't mean that it doesn't represent a hazard. So, and we will see, I'll show you a table where you can see some non-carcinogens, but are still toxic for humans. So our formula is a very simple formula, and the formula is for the hazard quotient. That is going to be the average daily dose during the exposure period divided by the reference dose, or the RFD. And we define the reference dose last class. So RFD is our reference dose. I will put it again just in case that you don't remember. The second term, so before I move to the second term, this is for one chemical, for a single. Let me put instead of one, for single chemicals. So every chemical is gonna have, and I call it HQ for short, a hazard quotient. Is gonna be associated with a single chemical. But what happens if we have if we are in a room that has some combination of multiple chemicals in the air, or maybe a cup of water that has a lot of chemicals inside of the water? Well, then every chemical is going to have an HQ, but how can we determine the hazard of all of those together? We need to calculate the hazard index. And the hazard index is going to be the sum of the HQ. So it's pretty simple, the sum of them. If HI, which I call the hazard index, is less than 1, the water or air are safe. Okay, are safe to drink, right? Or air to inhale. That's what it means. So we're gonna be adding them up, and if the number is larger than 1, then we can say that it's not safe for exposure. Okay, so we're ready for problems now? Well, hope we are. The first one is a very simple one. It's gonna be problem number 1. Oh, by the way, I forgot. I wanted to tell you something important. Just in case that you don't know, because I know someone shared with me, not in this class, in a different class, they have a very small space, and the mouse is hidden somewhere, and it's really hard to mute or mute yourself when you have a question. Just in case that you don't know, if you press the space, no, the space bar or key, and hold it down, then you can unmute yourself, and then hold it down and talk, and then just let it go to the back again. So it's I don't know if that will work with your equipment, but it has been working so far. We use it in summertime with my class. So just in case that you have a limited space, I think that is a good feature to know. Okay, so I want to change pages because this is fading already. Let's do problem number 1, and actually let me go to the handout. We're going to be doing problem number 1, where we have a carcinogenic VOC. VOC stands for a volatile organic carbon. So are we talking about a gas, or is a chemical dissolved in water? It's a gas.
Yes.
There you go. If someone doesn't know, how do we know it's the gas? Just look at the units, milligrams per cubic meter. That's the way to express the concentration of chemicals in the air. All right. So we have a carcinogen that has the dose response curve shown in figure 4.1. It is right here. And then we know that the person is 7 kilograms and they're breathing 20 cubic meters per day of air containing 10 to the minus 3 milligrams per cubic meter of the VOC. So it's not specific about what VOC is, just one of the volatile organic compounds. And then throughout the whole life, find the cancer risk. And for that, you need first to determine the potency. Okay, so there is something here. We haven't defined the formula to determine risk, and it's asking us to find the risk. So let's define risk. Risk, if we put it as a formula, it's going to be equals to the CDI times the potency factor. So make sure that you box the formula. This is a formula, and we're going to use it here. So we need to find the risk. What we're looking for is risk, so we don't know this one. Do we know PF, potency factor?
No, we don't.
Okay, we don't know it. Do we know how to calculate potency factor?
Yeah.
Yes, how do we calculate potency factor?
It would be the incremental lifetime cancer risk over the chronic daily intake.
Okay. Do we know the incremental lifetime risk?
Could we just?
It would be the same formula as the one you have written down.
So you're saying that this formula determine PF from this formula? Can you check your notes and see the formula that we wrote last time?
It would be the slope of the line.
There you go. It will be the slope of the line. If you look at the plot that you have in here, we have the risk and we have the dose. Okay, and the incremental lifetime is going to be this, right? The risk is going to be increasing because the dose is going to be increasing with time. And on the bottom, if you look at the formula that I gave you, is the incremental lifetime risk divided by the chronic daily intake, which is going to be similar to the dose. All right. So how do we determine PF? Can we use this plot to determine PF? But someone said the slope. So how do we calculate the slope in here? What numbers do you want to use?
0.3 over no, it'll be 0.003 over 0.3.
Okay, so you want to use the whole plot. It's fine. I like that too. Right? Some of you might be thinking, oh, I just want to use this little part. It should be the same ratio, so don't worry about it. So right now for PF, it's going to be calculated 0.003, which is the risk, divided by 0.3. And let me erase this in the middle so you don't get confused. I am actually using this one. So this is the 0.003, and then the other one is the 0.3. What is the answer here? Risk has no units. Dose has milligrams per kilogram per day. We need to always work with the units. PF is going to be equals to
0.01.
0.01, and our units are 1 over milligram per kilogram day. All right. Great, so now we have PF. Do we have CDI? Is it given? No, we don't have CDI. Can we calculate CDI?
Yeah.
Yes. I just gave you the formulas, right? Which one are we going to use? The one for water, the one for air?
The one for air.
CDI formula for air. Okay. I'm not going to write it down, but I'm going to talk about the terms. The first one is the concentration in milligrams per cubic meter. Do I have it? What is it?
10 to the negative 3.
10 to the negative 3 milligrams per cubic meter. And what is the next term of the equation?
Intake rate.
Intake rate. Do we have the intake rate?
Would it be the 20 meters cubed per day?
Yes, 20 cubic meters per day. If you notice the formula, the units were cubic meters per day, so it's similar to the flow rate. Okay, so it's 20 cubic meters per day. Perfect. What else?
Exposure.
What is exposure here?
70 kilograms.
The exposure, look at the units on the question that we brought.
70 years.
Okay, so it's gonna be over the 70 years, right? So
would we multiply that by 365?
So it's going to be the lifetime, 70 years in a lifetime. So we can have the 70 years, right? And then, well, let's put the 70 years and then just we need to convert that in days because it says exposure is going to be days per lifetime. So 70 years, which is in life, and then the 365 days, right? In a year. And then that will be canceling out. All right, divided by, someone says the body weight, 70 kilograms. And this is the weight of an adult. Anything else that I need to put in there according to the formula?
The 70 year per life.
The 70 year, okay. This is this is not exposure, just this is the expectancy of life. And we need to convert this into days. Because on the top we will have days, so we need to get rid of the years and put the days. So I'm just going to show you here that you could have noticed before that since it is the exposure is 70 years, this is going to be canceling out and you don't really need to include that in here. But be very careful. I didn't just cancel it out without telling you because sometimes the exposure is not going to be 70 years as we will see in a different problem. So just remember, this is related to exposure. So be very careful and don't cancel out just because it's 70 years of a lifetime. You need to be very careful and read. We'll see. We'll do a problem today. All right. So what is the CDI equals to?
I got 2.86 times 10 to the negative 4.
2.86. Can someone confirm?
Yes.
I confirm.
Okay, negative 4, you said, right?
Yes, to the negative 4.
Right, and the units?
Milligrams per day.
Milligrams per day. What about the kilogram?
All right, over kilogram.
Over kilogram, yes. And it's very important that cancel out your units and then you will see cubic meters going there. You have milligrams over kilogram, and then the days go on the bottom, right? So always, even if it is silly and you're super confident, units are gonna help you to double check that you're on track. Don't forget it, especially in this type of problems. So can we calculate now the risk? Yes, we got it. So we have CDI equals to 2.86 times 10 to the minus 4. And now I'm gonna add the units. Times PF 0.011 over milligram kilogram per day. What is the risk equals to? Okay, 2.86 times 10 to the minus 6. What units?
No units.
No units. We know that risk has no units, and also when we do the dimensional analysis, they are canceling out. So if you ever do your risk and at the end your units don't cancel out, then you did something wrong. That's an alarm, an alert, right? Like, hey, hold on. Okay, who can tell me, is this risk acceptable?
It's 1 and 3.5 million, so it would be acceptable.
It is? Okay, so hold on. What is APA?
1 in 1 million.
So it's larger or smaller than 1?
It's larger.
So it's acceptable?
No.
So it's not acceptable. Always remember, let's compare to this. Unless, now, let me hold in here. In the class, I'm going to use the 1 to times 10 to the minus 6 to compare. There could be other instances where that might be a different number. Okay, so just for the class, that's what we're going to use. Later in life, in practice, if you find something different, for whatever reason is, it will be fine. Even smaller number. EPA is a national standard, but states sometimes have they have a stringent requirements. So this is larger than EPA, so not acceptable.
I have a different, I think it's 10 to the negative 7.
Oh, you have.
When it's 6 times 10 to the negative 7.
Can someone double check, or everybody else gets 10 to the minus 6?
Yeah, I got the minus 6.
0.01.
Okay.
You double check your calcs. And so I'm gonna go by the majority, the group. I think that we are double checking calculations here. But if it was to the minus 7, this is a small number and would be acceptable. All right, so that's important. Okay, so problem number 1 is done. We're gonna be using these formulas again and again and again, just slightly different problems. So this is a long problem with a lot of different parts. It's gonna take some time to get it done. And alrighty, let's start. It's very lengthy. Let's read it carefully. Let's make sure that we understand what's happening. And then, until then, we're going to be proceeding to solve the problem. And also, I'm going to be introducing you some tables to ensure that you remember how to use them. I mean, that you learn how to use them. We have a city that has a water supply with a 0.02 ppb, and then they give us a conversion factor. 1 ppb is equal to 10 to the minus 3 milligrams per liter of polychlorinated biphenyls, or PCBs. Using the PCB oral slope factor, 7.7 milligrams per kilogram day, 1 over all of this to the minus 1. Do you recognize this slope factor? Look at the units. Does that remind you of something?
Is it second order?
No, it's not a reaction rate. The units are 1.
It is the PF.
Yes, the potency factor. Here in this problem, they call it a slope factor because it comes from the slope. So this is the PF. Yes. Always remember the units are going to be giving you a lot of information. So if sometimes you don't know what it is, just look at the units. And the EPA recommends exposure factors given in table 4.10. From your textbook, we're going to use table 4.10. It's shown below here. I'll show it to you. And also says, note that the potency factors can be found in table 4.9. So let me go to the PowerPoint, and I'm going to just show you table 4.9, where we can see the potency factors for oral route and potency factors for inhalation. The units are similar. The difference is that the chemical might be in air or water. That's the only difference. And some chemicals can be either in water or air. Some chemicals could be in both phases. So like arsenic, it could be both on the water or the air. And don't use the same potency factor because the effect is going to be slightly longer depending on how you ingest the chemical. And if you remember categories, look, it's A, carcinogen, right? Or B2, or B1, or C. So here is one of the examples where you could learn a little bit more about the carcinogenic property or tag that the chemicals could have regarding EPA classification. So remember table 4.9 on your notes, reading notes. You don't need to copy paste this table. That for me, that would be a waste of your space. If you need it, either give you the number or give you the table in the test, or tell you that you need to print it out, all right, or have it available. So please remember, for the reading notes, I don't think that this is needed. You need other type of information. And then we have in here, this is for 10. I'm gonna go back to the handout because we have the table already on the handout. We're gonna need it. Okay. Oof. So we know that the problem is this on the air water. How is people being exposed to the PCB in this problem?
Water supply.
In the drinking water, all right? I just got thirsty of thinking about drinking water. So it's gonna be coming in this water supply, the tap water. So let's see what's the situation in here. What will be the individual lifetime cancer risk for an adult residential customer? So we're gonna be calculating the risk for an adult living in a house, in a household, for the lifetime. So individual lifetime cancer risk. In this case, it's very specific about calculating the cancer risk for this person. And we need to remember these characteristics. So let's go ahead. We are gonna be talking about calculating risk. What is the formula for risk?
CDI multiplied by potency factor.
Okay, so CDI times the potency factor, and we're talking about the risk. This is part A. Can I determine PF?
It's
we already have
given.
it.
Is
It's
it
given.
okay? What is it? Okay, 7.7. All right. What about CDI? Can I determine CDI? Yes, we have a formula. So PF is given. We got it. CDI, we have a formula. We need to use it. So let's determine CDI. But actually, before determining CDI, let's read this table. The contaminant is found in water, potable water. We're talking about an adult. Do we have the exposure frequency here? For this table is 365 days per year. And then it says 30 years, and the body weight is 70 kilograms per day. So when you have no information about the exposure and frequency, this table is very, very handy because they give you the average exposure, or what the EPA considers a good way to consider red risk. If the statement gives you information that is more specific about a situation, you can come in here and use the whatever information is missing from the statement. Okay, so we're gonna use this information. We have it highlighted in there, and we're gonna use that to calculate the CDI. Okay, so I can keep it in there so I don't need to write it down to calculate CDI. So let's calculate CDI. What is the concentration? And remember, it has to be in milligrams per liter.
It would be 2.2 times 10 to the negative 3 milligrams per liter.
Okay, 0.2 times 10 to the minus 3 milligrams per liter. Perfect. Times. The formula says that we need
Liters.
the intake rate is 2 liters. Perfect. All right. And this is daily intake, correct? And the next part of the formula says exposure. What is exposure?
It's 350 days per year.
350 days per year. All right. And for how long?
30 years.
For 30 years. Okay. Good. 30 years in their life. Okay. Now on the bottom, we're gonna have 70 kilograms, which is the body weight. It's an adult. If it's a child, it's gonna be 15. That was given on the statement. Times how long? What is the lifetime?
70
70.
years.
70 years. Times 365 days. All right. So in here, I really like to cancel everything. So let's go and cancel things. We have days, they go away. We have years, they go away. We have liters going away. In the bottom, we have years. And then lifetime is going to be canceling out. It's on the top and the bottom. We end up with milligrams divided by kilogram per day as we need to. And if someone can tell me what is the answer for CDI?
I'm getting 2.35 times 10 to the negative 6.
Okay, 2.25 times 10 to the negative 6. Can we have a confirmation? Someone says times 10 to the negative 3.
No, I've got the same to negative 6.
Negative 6. Everybody negative 6?
I got
Yes.
negative 6.
Yep.
Okay, so everybody got negative 6. So make sure that you have 0.2 times 10 to the minus 3. You have 2 times 10 to the minus 3. That could be the problem. Alrighty, so we're going to go with 2.35 times 10 to the minus 6. And we know PF. So let's calculate the risk. I'm going to put it in here on the bottom before we move to the next page. So we have part A completed. So it's going to be 2.35 times 10 to the minus 6. I don't have a space for the units. I'm going to put them on the bottom. And then PF was 7.7, I believe. And all of this is 1 over milligrams per kilogram per day. Hopefully you have a space to have the units. They cancel out. Discard the 3 here. It's the page number. And what do we have for the risk?
I got 1.81 times 10 to the negative 5th.
I'm going to put it on the top here. Risk 1.85.
No, 81.
A1 times 10 to the minus 6. Can someone tell
Oh, no,
me?
to the negative 5th.
Negative 5th.
Yeah.
Right. Thank you. Confirm?
I got
I
the
got the
same.
same thing.
All right. Perfect. So is this risk acceptable?
Yeah.
No, it
Because
isn't.
this
It's bigger
Smaller.
than 1 and
is smaller than 1 times 10 to the minus 6. Are you sure? No? Yes? 1 times 10 to the minus 6. Which one is smaller?
The one to the negative 6 is smaller.
Yes. So it's larger, right? So it's not acceptable. So it's very important that sometimes if you need to write the 1.0000018 and then compare them, 1, 2, 3, 4, 5, right? Do it. If that's what you need to make sure that you're sure, do it like that. Because yes, this exponential number, these numbers that are very small sometimes are a little bit confusing. So the risk is not acceptable. Let's just put it in here. The risk is not acceptable. All right, I'm sorry I was very messy here, everything together, but I didn't want to just to go to another page. All right, so we have part A. I'm going to scroll up and read part B, and then part B has to be done in a different place. Let's read part B. So now we have the risk. Now, if you notice, when we calculated the risk, we divided by the 70 years of a lifetime. So it's the risk over the 70 years of life of a given person. Now, in the next question, it says that in a city of 1 million people, we need to use this risk assessment to estimate the number of extra cancers per year caused by PCBs in the water supply. Extra cancer refers to those cancers caused by PCBs as opposed to cancer caused by any other thing. An example is smoking. So even if we didn't have any PCBs in the water supply, there was going to be some cancers happening. And the PCB present on the drinking water system is increasing that number of cancers. So it's just calling this cancer to PCB as the extra cancers. So we need to calculate the number of cancers that are going to be a result because of the presence of the PCB. All right, so we're going to be bringing this number that we just calculated, 1.81 times 10 to the 5th. Let me just go to a different page. If we put this number as a fraction, if we put, and remember, the EPA refers to 1 over a million, right? If we put the 1.8 times 10 to the minus, was it 5? I already forgot.
Yes, it was 5.
Okay, thank you. If we put it as a fraction, what number do you get? 180 or 18 over a million?
I think it's 18 over a million.
Okay, it's gonna be 18 over 1 million. So this is the same number, and we're gonna be using this in this problem. All right, so the population in the city was 1 times 10 to the 6 is 1 million. It's not the same as the EPA risk, it's just the number of people. And the risk to have the cancer to the PCB, it's a number, no units, so it's 18 over 1 times 10 to the 6, or the million, right? Remember, this is our risk. And then this is the risk in 70 years, right? Over 70 years of the life of someone. So we need to divide the risk by 70. If we do all these calculations, we are gonna get the number of cancers. When we do this fraction, what we are putting in here is 18 cancers due to PCB. Okay, those will be the units in 1,000 people. So this is people, and this is people, remember. So how many cancers do we have per year? In a city of 1 million people. One times 10 to the 6 times 18 divided by the million, or you can just go to the 1.8 times 10 to the minus 5. I'm just expanding this in here, divided by the 70 years.
I got 0.26.
Agreed.
0.26 cancers per year. Is this a lot?
No.
So someone is saying no with question mark, right? So to say it's a cancer, even if it's 0.6, it's a lot. If you are the person that is affected, right? So it doesn't seem to be a big number, but it's still that represents people. So no, thankfully doesn't seem to be a big number. So this is what it was asking us to do. In a city of 1 million, then let's calculate the extra cancers. So all the other cancers, the number will be increased only by 0.26 cancers per year in a city of 1 million people. Now, this problem could be done if we change the number of the people in the city, 100 people, little town, maybe 500 people, 10,000, 25,000 people. I'm just using what was on the textbook as for the calculation. Now, so we're done with this part. Now, part C says, assume that the average cancer death rate in the United States, now it's giving us the average cancer death rate, is 193 cancers or people dying from cancer per 100,000 people per year. How many cancer deaths will be expected in a city of 1 million? All right. So we're going to be bringing the 193 over 100,000 and the 1 million city to solve this problem. So this was part B. Let's do part C now. In part C, it's telling us that we need to do the calculation of the total cancer deaths or deaths due to cancer. And we know that we have 193 cancer deaths, right, per year in 100,000 people. This is all the deaths due to cancer, and the city was 1 million, or 1 times 10 to the 6 people. All right. Can you tell me how many deaths do you have? Pretty straightforward. Canceling out. Multiply by 10. No, divide by 10. 19. Am I doing it right?
I got 1,930.
Yes, 1,930. Thank you so much. Okay, cancer deaths, right? Per year. So, in the city of 1 million people with that national rate cancer death, we will have very close to 2,000 people dying from cancer every year. That's really, really sad. And I think that's it on part C. Let's do part C. I'm sorry, D. Part D says, do you think that the incremental increase cancer caused by PCBs in drinking water will be detectable? How do we know? How can we determine if the number of deaths due to PCB are detectable? Let's look at the numbers. The cancer, right? Everything else, all the cancers in that city is going to be about 2,000 people. But also we know that in a city of 1 million people, we have 0.26 cancers per year. Is it significant? Is it detectable?
No.
It will not be detectable, right? It's very, very tiny. Numerically, how can you prove that it's not detectable? What would you do? What would you do, engineer? You say, no, you say, no, it's not detectable. And then the people is like, why? Show me. Well, assuming, right, that all people that gets cancer due to the PCB dies, and you add this in here, and you calculate all the cancer deaths per year. That give you a total of 1930.26 cancer deaths per year. It's very significant. I've been rounding up to 2,000. There's another way. 0.26 divided by 1930 times 100, what do you get?
0.013.
0.013% of deaths due to PCB in drinking water. Will this number be good enough to say or to recommend, oh, don't worry about the PCB in drinking water. Look, 0.013%, it's fine. What do you think?
Doesn't it kind of depend on the population? Like if it's a really huge population, then that would be an issue. But
Okay, so what is the population in here?
1 million.
$1 million. $1 million. Oh my gosh, people. Well, $1 million. Every person is very valuable. Yes. So yes, I know you're right, Anderson. It comes down to the population, but just when we look at if a politician comes and says the PCB in drinking water is not important because it's only 0.13% of the deaths caused by cancer, we don't really know what's the context, right? So we will need to have more information. So still, no matter how little the percent is, that means someone is being affected due to the presence of that PCB in water, even if it is long term. We're talking about chronic exposure. So this problem is very interesting, is very complex. There's a lot of different parts. Please go back and check it out. Do the other problems that are solved on the textbook. They are all different. Different things are coming into place. The most important thing, make sure that you practice with the tables, getting those numbers down on paper, and using the information given on the statement too. Because sometimes you don't need all the information on the table. It's given on the statement. And we're gonna do problem number 3. What time is it? Oh, it's 3:17. Well, let's read problem number 2, and then we're gonna number 3, and we're gonna stop to get ready for the quiz. Problem number 3. So we're not gonna be able to finish risk, but our quiz is gonna be on. Oh man, it was on the agenda, and I just forgot. The 28th, I believe. I'm trying to look for the agenda. Okay, look, let's read this, and I'll remind you. On Monday it's on the agenda of the date. We have a man that works in the aluminum smelter for 10 years. So this person is working for 10 years there. The drinking water in the smelter contains arsenic at a concentration of 0.07 milligrams per liter and methylene chloride. Oh my goodness, it's a lot of very nasty chemicals. 0.56 milligrams per liter. His only exposure to this chemical is at work. So this is one of those occasions where I'm telling you, you need to look at the context of the problem and use that information. Exposure is 10 years, only at work. What is the hazard index or HI associated with this exposure? And does the HI indicate that this is safe? Is that safe level of exposure? And what is the incremental risk, lifetime cancer risk for the men just due to the drinking water at work? And if is this acceptable according to EPA? So we're gonna be doing a lot of work next class. Make sure that you get all your tables ready and the questions, because I'm gonna be bringing those and we're gonna solve this problem. Alrighty, so I wanna stop here because we need to get ready for the quiz. The quiz officially is gonna start at 3:25, so we have 5 minutes. I wanna make sure that I go over a few things. Make sure that everybody feels prepared for the quiz. If you go to Blackboard, the exam and quiz tab is already open, available for you to look at it. It was since this morning, so everybody should be looking at it. And if you click on the quick exams and quizzes, the quizzes folder is also open. The one thing that is not there is a quiz. Well, the folder, it's in there. Please read the instructions. And I'm gonna give you 2 minutes to read the instructions, and then I'm gonna give you other instructions to get ready for the quiz.
Professor,
Yes.
are we allowed to use Excel?
No. No, I would have sent you an email telling you about Excel. I need to give you a warning on that.
So,
Some students connect on phone or tablets and you cannot use Excel, so no. It doesn't say Excel in there.
Do you need to account for freeboard in a plug reactor?
I will say I look at the question. Look at the question, what is asking you. If you are designing, yes, you need to account for freeboard, right? If you're asking for the volume of a tank.
But a plug reactor isn't necessarily a tank?
A plug reactor, we draw it as a pipe, but it could be a regular tank. It's always gonna need a freeboard. Since you don't know, you can assume that it's a tank or not. Depends on the question. Just tell me what you are doing, just to make sure that I understand what you're doing. All right? Okay, so everybody has read. Very similar, nothing changed. Now, the only thing that is different is that I'm gonna give you total 22 minutes. It's not 22 minutes to solve the quiz, 15 minutes to solve the quiz and 7 minutes to scan your work. Now I'm gonna come with the other thing that you will see once you start the quiz. We still have 3 minutes, so please pay attention, it's very important. The quiz is going to be asking you to submit your work. But there are 2 questions where you need to enter the answer on Blackboard. For those questions, I don't need to have your work if you don't want to. I would prefer that you submit your work. You could get extra credit if anything, maybe not. Depends on what is in there, right? And that you submit doesn't mean that you're gonna get extra credit. And you can submit everything on the same question. There is one question that you can submit, you can go back and forth and look for it. If you choose to use more than 50 minutes on the quiz and you end up not being able to submit, I am not gonna take your work, so please manage your time. It should give you enough time. During the exam, someone had a fatal issue and I was able to work that out with the person individually. If you have some very situation, your computer stopped working and you're out, take a photo, timestamp as soon as you can, log in. If the class is over, don't worry, send me an email, let me know, and I'll work out with you. I have another class coming after this, so probably I will not respond right after, so don't be scared. I'll work out with you. I just need to use timestamp things. But I don't think that is going to be an issue. So that was during the exam, and we worked it out really well. So remember, the test is going to require you to enter answers. Please enter answers to those questions that you need to enter the answer. One of the questions has 3 parts, A, B, and C. Part A and B require you to upload your work. The good news is, for any reason you don't want to upload the work or something happens, you didn't time yourself well, it's only 30% of the quiz. So as long as you have confidence on your work, the 70% that you submit on the box is going to be good. So it's a lot of redundancy, different ways, just in case to cover for any issues that we have. Okay, so in a minute, the quiz is coming. As soon as you're done, you can disconnect. Don't worry about it. At 3:25, just refresh your browser. Remember, at the moment when you click is when you have, your time starts counting. Okay?
We upload our reading notes to the quiz directly, right?
Reading notes are not gonna be used for today.
Oh, okay.
No reading notes for this one. Starting risk assessment. All right? Right now, no reading notes. Do only